In this lecture, we're gonna talk about the fundamentals of spectroscopy. And the key learning outcome that I'd like you to acquire is to understand the basic theoretical background and the overarching fundamentals of spectroscopy that cuts across the many different types of spectroscopies available, and there are many different types of spectroscopies out there. Now, all analytical instrumentation, and of course spectroscopy is one big segment of analytical instrumentations out there, but all analytical instrumentations, they are based on this premise, that you've got an energy source, and then you've got, the analyte or the sample that you're trying to analyze, and the energy source impinges on the analyte, and because of that chemical perturbation, you look at the response, from that energy, and that's what you detect, using different types of detectors. Now, in most cases, you're gonna see the energy source that is very common out there is light. So light heats a sample, and of course, we know when light impinges on a sample, which has got different chemical constituents. The light, can be, for example, absorbed. A portion of the light can be absorbed. A portion of the light, can be scattered. Can be scattered, and so on. And then you can look at the light, that is actually, transmitted. Okay. And so the basis of that, for example, is absorbance spectroscopy. Like I've said, some of the light can also be scattered. And when you're doing detection of light that is scattered, the spectroscopic technique, is called Raman spectroscopy. Okay, and so on. So there are many different types of spectroscopies out there. But the typical instrument, like I've said, contains an energy source. In spectroscopy, that would be a light source. Of course, the analyte that is being analyzed, and then a detector is another heart of the instrument. And of course, the data often these days is transmitted, to a computer. Okay, so take note of that fundamental aspect of all instrumentation devices out there. And of course, take note of this also. The detector typically would be converting, the energy source often, into an electrical signal that you can easily measure. Because of course, most computers are electronic devices. So often the detector would be converting light into an electrical signal. And sometimes that's why we call detectors as transducers, because they are converting a non-electrical quantity such as light into an electrical quantity. So essentially this slide, sort of covers just the basic premise of all analytical devices out there, be it spectroscopy, be it electrochemistry, be it mass spectroscopy, and so forth. Now, of course, in spectroscopy, the energy source, as I have said, is electromagnetic radiation, or light. Now, remember, light is a continuum of different energies of electromagnetic radiation. Of course, you've got, different types of these radiations, such as the gamma rays. You've got the X-rays, and of course, these ones are very high energy, penetrative, kinds of radiations. And then you've got, the UV, which is next in terms of energy, to the X-ray. You've got the visible light, the light that we see. You've got the infrared, which is the light on your stove, for example. When you heat a black body, it becomes red hot, and that is infrared radiation. And of course, all of us use microwaves. Whatever radiation you use in a microwave, is a microwave type of radiation, and of course, the lowest energy is the radio waves. Now, all these types of light, can actually result into a spectroscopic technique. All of them can. You can have X-ray spectroscopy, you can have, even microwave spectroscopy and so on. But in most cases, you're going to see, these three, form the basis of most spectroscopic techniques. And that's why sometimes they are called, the optical methods. Okay? And take note of the following. If at all I've got, as I've said before, you've got light impinging on a chemical. Now, within the electronic level of that chemical, there are lots of things that are happening after the light hits, those chemicals. For example, if at all you're dealing with an X-ray, the X-ray is penetrative, and so it's gonna excite the inner electrons, of the chemical species. If at all you're dealing with the UV radiation, the UV radiation is going to excite, all right, or influence, the behavior of the outermost electrons, which are called the bonding electrons. Often it's going to excite them, to a higher energy level, and so on. And so all of these, types of light, result into different types of spectroscopies, as I have mentioned. And so it's important, for us to remember that premise. If I heat a sample with these types of energies, what types of transitions or electronic transitions are happening within a molecule? As I've said, with the X-ray, you're breaking the bonds and you're ending up with excitation of the inner electrons because I've broken down the bonding electrons. And so X-ray really is a good technique, when you're trying to analyze elements, okay? So it's not very useful if at all you're trying to analyze molecules, because the X-ray is gonna break down the bonding electrons that results into making molecules. So X-ray typically, is often used to analysis of elements, all right? So this region, the optical spectroscopic region, the UV, remember the UV is not strong enough to break the bonds in most cases. And so typically it would cause electronic transition of the outermost electrons. And so that's what happens to the molecule, electronic excitation. In the visible range also, you get electronic excitation of the outermost electrons, or what you call the bonding electrons. In the infrared range, they are not energetic enough to cause electronic excitation. And instead, they cause vibrations, of the bonding electrons, the vibration and rotation of the bonding electrons. The microwave, on the other hand, is very, very weak. It causes the rotation, of the bonding electrons. And that is why, we use microwaves to heat food, because when you are rotating bonds, they generate heat, okay? But remember, not all compounds out there respond to microwave. For example, if you take hexane as a solvent and throw it in the microwave, it never heats up. And the reason for that is the bonds have to have a dipole moment. So the bonds must have a dipole moment, okay, for them, to respond, to microwave. And so often, the bonds have to be polar, in some way for you to use microwave, for heating. But again, the key thing is, you are rotating the bonding electrons. So take note of that in terms of what happens when electromagnetic radiation impinges, on a chemical. If at all is X-ray, breaking of bonds, okay, outer bonds. and instead you've got inner electrons, being excited. The optical range, here the UV excitation of the electronic, rather the bonding electrons. Visible range, excitation of the bonding electrons. The infrared, vibration, of the bonding electrons. And lastly, microwave, you've got the rotation, of the bonding electrons. Now, in terms of the spectral signature of the atoms, and the molecules, they are typically very different. If at all I've got, an atom, such as, say, sodium, for example, it's going to behave very different, than if I've got, a molecule, such as benzene. And this is why. Now, sodium or any other atom out there, it has electronic states. You can see the E1, the E2, all those are electronic states or energy levels. But they do not have, rotational and vibrational levels. And as such, if at all I've got light, that is hitting on a sodium atom, for example, that light get excited, or the electrons, get excited between electronic states. And so if at all you got a spectra that is resulting, you end up with a line spectra. So atoms give you a line emission spectra, and the reason for that is because they only have electronic states and they do not have any rotational or vibrational states. Okay. On the other hand, molecules have electronic states, but in each of these electronic states, you've got, vibrational states. In each of these vibrational states, you've got rotational states. So essentially, we are saying at an electronic level, molecules are very, very complex. And so that means, the electrons can transition in very complex ways, between electronic states, between vibrational states, between rotational states, and so on. And so the spectra that you actually get from molecules is not a line spectra. Instead, is a peak, often is a band kind of spectra. Reason being, there are lots of possible transitions, that could take place because of the presence of rotational, vibrational, and electronic states as well. And so this slide, essentially repeats what I've just said, in molecules. If at all I've got some energy that is absorbed, light energy absorbed, causing, electronic excitations, all this could be happening, because, they are present in the molecular structure. In the atoms, on the other hand, you just have electronic levels, and so the spectra you get for atoms is very, very simple. It's only a line spectra. Okay, that's intensity. For molecule, on the other hand, I typically would get, a much more complex spectra, which is a band like that. And so as I've said, if at all I've got a molecule, such as beta carotene here, I think it is, I'm gonna have a very non-characteristic, type of spectra, because the molecule is very, very complex. And so there's so many possible transitions that would take place in this case. And so the more complex the structure, the higher the molecular weight, the more you would get more a very undefined kind of spectrum. Look at this, you've got caffeine on the other hand. You can see the kind of band that I get is not very, very broad and complex, because you don't have a very big molecule. On the other hand, compared to beta carotene, you can see I've got a much bigger band, because there are so many different possible transitions. Look at acetone, for example. It can only absorb within a very narrow range, 230, to about 300 nanometers in the UV range. Because as you can see, you know, it doesn't have a lot of many possible transitions because it's a very small molecule. Okay, and so you're gonna see compounds that have got very big chemical structures, you know, they often, you know, would be colored. And the reason they are colored, you know, is because they are likely, you know, to absorb the visible radiation. So that's why beta carotene is colored and so on. But hexane is not colored because it's not absorbing anything, you know, in the visible range and so on. So as you can see, it's very difficult, you know, to really find a lot of information sometimes just by merely looking, you know, at a very complex molecule in terms of its spectra, because the spectra seems very undefined. It's just a hump. But sometimes, you know, we often use the spectra as a cursory, at a very cursory level, you know, to differentiate different types of compounds. So what I'm saying is absorption spectra is not very definitive when you're trying to do differentiation of different types of compounds, because it's not very nicely defined unless, you know, you're dealing with drastically different types of chemicals, you know, such as, say, retinol or beta carotene compared to acetone. But if the compounds are very closely related, you may not be able at all, you know, to see any major differences in the spectrum. And as such, you know, the solution to these is separation. So that's why in almost all cases, you know, when you're dealing with a very complex kind of, you know, sample, you have to do HPLC, you know, and then now you've got, you know, an absorption detector, you know, such as a UV detector in the end, so that you do the separation first, you know, before detection. So let me quickly remind you, you know, that at an electronic level, why do compounds absorb? What's happening? Why do compounds absorb radiation and some do not? For example, if at all I've got a solution such as, say, acetone, why does acetone, you know, not absorb in the visible range? Okay, it's good to be reminded, you know, about, you know, the molecular orbital theory, okay, of absorptions that are energetically unfavored and absorptions that are energetically favored. Okay, if at all I've got a molecule, a straight chain hydrocarbon, we know the electrons that are present are only occupied, you know, in the sigma orbitals. Okay, and they do not have any pi orbitals, they do not have any n or non-bonding orbitals, you know, and so forth. And so for that reason, you know, hydrocarbons, you know, typically do not absorb, you know, visible radiation, because the transition, say, from the sigma, you know, to the sigma star is a very, very large transition. It's not energetically favored. So for that reason, you're gonna see compounds, you know, that are conjugated. You know, they've got a double bond, meaning they've got a pi orbital. You know, compounds, you know, that have got a double bond and maybe they've got, you know, a lone pair of electrons, you know, such as oxygen. Often these compounds would often be colored. And the reason they are colored is because, you know, the energy transitions are favored. For example, if at all I've got a compound like this, carbon-carbon double bond, it means there are electrons in the pi orbital, and so I can excite those electrons easily to the pi star or to the pi antibonding orbital, because the energy gap is not very, very large, and so they are favored. If at all I've got electrons in the non-bonding orbitals, for example, in the case of oxygen, and alcohol, for example, I can easily excite those electrons, for example, you know, to the pi star, if at all I've got a double bond and so on. So it's good for you guys to remember a little bit, you know, about this molecular orbital diagram, because it explains to you why it's possible to see some reagents being colored and some reagents not colored, and it's all based on the transitions, electronic transitions in the molecule that are allowed, because, you know, the energy levels are not very different, and the transitions that are not allowed. So what are some of the factors, that affect, an absorption spectra? As I've mentioned, often it's how big, how complicated, the molecule is. If at all I've got, say a very simple element, I essentially get a very simple spectra, which is a line spectrum. You can see the peaks are very sharp. It's a line spectrum. If at all I've got a benzene vapor, for example, it's vapor. I don't have a solvent. Again, you can see that I get a fairly characteristic spectra as well. If at all I add a solvent to benzene, now you can see there are much more transitions that would be taking place, and so my absorption spectra becomes a little less defined. You can see the peak starts to broaden because there are many transitions that are taking place. On the other hand, if I take biphenyl, which are two benzene rings, fused together, now you can see my spectra becomes even more less defined. It becomes a simple hump, because there are many, many possible transitions that would be taking place. So very quickly, let's talk about the spectrometer in terms of its components. As I have said before, its component is very typical of any analytical instrument. You've got an energy source, which is light in this case. You've got a monochromator, and the monochromator is only a wavelength selector, so that you've got only one single beam of radiation passing through. And then you've got my sample, and some of the light is absorbed by the sample, but some of it is transmitted. And so essentially you are detecting the transmitted light, using your detector. So you're detecting the transmitted light. And so the relationship, for spectrometers in general is the Bayes law. Absorbance, is proportional, to concentration. And the proportionality constant is what you refer to as the molar absorptivity. And the molar absorptivity determines the extent to which the molecule absorbs light. And B, as you well know, that would be the path length. B is a path length. As I've said, the spectrometers, you are detecting transmitted light. And yet we call it absorbance spectroscopy. So what is the relationship between transmission and absorbance? And I think you can see it right here. The relationship is absorbance is equals to the negative log, of transmittance. So if I know transmittance, I can easily calculate absorbance, using that relationship. So if I give you a problem like this, I think it's very straightforward. Calculate the molar absorptivity, having been given each of these parameters. Essentially, you just invoke, the Bayes law, and you can calculate your molar absorptivity. I think it's fairly straightforward, okay? And if I ask you to determine the transmittance, you know the relationship. You are told I have absorbance, the transmittance is determined, by that relationship, okay? So if I'm looking for transmittance is equals to 10 raised to the power of negative A, which is absorbance. And so you can easily determine that. So fairly straightforward type of calculations. I don't need to spend a lot of time on that. So what are the types of errors, that are pertinent or common with spectrometers, based on the Bayes law? So you're going to see spectrometers are not very, the limits of detection, are fairly high, meaning they are not very sensitive, okay? And there are a couple of reasons, why they are not very sensitive, okay? Now, one reason is they're very prone, to electrical noise. Now, that's one big problem, especially because you're using a detector, and detector is an electrical, is a transducer. And of course, because you're using light can pass through to the detector without necessarily, going through the sample. So because of that, you always tend to get a bit of noise, even when you're not analyzing anything. and that's what you refer to as electrical noise, okay? And that's often, from stray light hitting the detector. Now, another important thing is, the fact that you can only use spectrometer, when the absorbance is in the range of around, 0.1, to about 0.9. Anything beyond that is not linear. So you want your absorbance, to be around 0.1 and around 0.9. After that, it plateaus off. And that's why I said it's got a very low, should I say dynamic range. It's a very low dynamic range. The limit of linearity to the limit of quantification, is not very wide. Other things that affect, the spectrometer would be the cuvette, the way you position the cuvette. If you don't position the cuvette the same way each time, then you get a lot of irreproducibility. That's why when you guys did it in the lab, the imprecision, the standard deviation was reasonably high, because each time you put the cuvette, chances are you're going to put it in a slightly different position. Any dust, that is present, on your cuvette equally scatters light. And of course that affects, your limit of detection as well. Maybe one other big challenge is the following. It's not very good, for analyzing high concentration samples, because with high concentration samples, this tends to happen. High concentration samples tend to form dimers and so on, and the molecular absorptivity, of dimers, is very different, than if you have a single molecule. Dimers just refers to two compounds fusing together. Now, another big problem is the fact that you need a monochromatic beam of radiation. There's no single monochromator out there or wavelength selector out there that is perfect. So again, that affects your limit of detection. Maybe one other major significant deficiency, spectrometers, is the fact that you can't really use it to analyze weak acids and weak bases. Anything that undergoes chemical equilibrium, meaning it dissociates and so on, during the experiment, it means you cannot use spectrometer, okay? Unless you try to equilibrate it and make sure you're not getting, these chemical equilibrium taking place. So for example, if at all you're analyzing weak acids and bases, always make sure you buffer, you add a buffer to the sample, so that you sort of, make sure you're not getting, these acid-base equilibria, that is taking place. Because remember, acids and their conjugate bases and so on, they would have different molar absorptivities. And so that's why you can't really use it, without buffering the system. So that's a solution, to buffer. So if at all I was analyzing aspirin, dextromethorphan, ibuprofen, and so on using spectrometer, then I should always add a buffer. So other than absorption spectroscopy, you also have other types of, spectroscopies. So remember, absorption spectroscopy, like I have said, is based on electrons, transitioning from low energy level to a higher energy level, after the molecule absorbs light. But remember, electrons, never stay in high energy levels. They are very unstable. And so because of that, they tend to relax back, to the low energy levels. With that relaxation, light is emitted, okay? So other than absorption spectroscopy, you also have emission spectroscopy. The light, that is emitted following an event of absorption, okay? So emission spectroscopy. So there are two types of emission spectroscopies out there. So there's what I'm calling F, which is fluorescence spectroscopy. And there's what I'm calling the P, which is phosphorescence spectroscopy. So those are two different, types of emission, spectroscopies. Now, take note of this so-called Jablonski diagram. Before fluorescence spectroscopy happens, in most cases, you have what they refer to as, an electron coming from a singlet, down to the ground state. So in most cases, fluorescence is only specific, for molecules out there, that afford a singlet, a state, in their molecular orbital system. Before phosphorescence happens, you can see there's another transition. An electron can be excited to a singlet, but it can transition to a triplet that is of equal energy. And that transition from a singlet to a triplet is what they refer to as intersystem crossing. And so for phosphorescence to happen, you actually need these intersystem crossing, to happen. And so this one is very, very rare. There are very, very rare types of molecules that afford these types of transitions. And those molecules, typically, for them to afford this, they need to be very conjugated. They need to have lots of different bonding bonds, that are present. So if I may summarize, for phosphorescence, to happen, you need intersystem crossing. So phosphorescence is much rare compared to fluorescence, and fluorescence is more rare compared, to absorbance. So in terms of selectivity, then I would say fluorescence and phosphorescence are fairly selective technique because you don't have too many compounds out there that undergo fluorescence and phosphorescence. So those compounds must be very conjugated. They must be big molecules. So look at the spectra, the emission spectra, of phosphorescence compared to fluorescence. As you can see, now the fluorescence, would be of higher energy, compared to phosphorescence. Because if you look at the Jablonski diagram, the intersystem crossing also results into loss of energy. And because I'm losing some energy, that's why phosphorescence has got, a lower energy gap, compared, to fluorescence. So you can see in terms of limits of detection, then you would say fluorescence, has got a larger or a lower limit of detection, meaning it's more sensitive, compared, to phosphorescence, so less sensitive. And the reason it's less sensitive again, is because, the energy strength that hits the detector, for phosphorescence is lower compared to fluorescence, okay? And I think I've already said that here. However, phosphorescence, is more selective. Is more selective, compared to fluorescence, because again, as I've said, there are very few molecules, that undergo phosphorescence because of this requirement, of a triplet, that has got an equal energy, to a singlet. So when you're making an emission spectrometer, or what you refer to as, luminescence spectroscopy in general, okay, emission spectrometers, you can see the difference between absorbance spectrometers and emission spectrometers in terms of the configuration of the components. Take note of that. The configuration is different. As you can see with the absorbance, I had the light source, the monochronometer, the sample, and the detector, was around there. It was in linear fashion. However, with fluorescence or emission spectrometers, you can see the detector, it's at right angle, is at a right angle, to the light source, okay? And you can see why, because I do not want the interference, from the light source, for the fluorescence, okay? All I want is the energy to actually come, from the emitted radiation following the perturbation, from the light source. So take note of that configuration difference between emission spectroscopy and absorbance spectroscopy. Absorbance spectroscopy, as you remember, the detector is linear, to the light source. It's in line to the light source. In emission, it's in right angles. It's important, to take note of this relationship, but that before fluorescence takes place, you really need absorption to take place, because the energy is essentially coming, from the light, that was absorbed, okay? And if you look at the profile, the emission profile compared to the absorption profile, they are always mirror images. They're always mirror images. The only difference is, the emitted spectra is shifted red, is red shifted. And the reason it's red shifted, you can see it's of lower energy, compared, to the absorption spectrum. And that makes sense, if you look again at the Jablonski diagram, you can see that some of the energy is gonna be lost due to radiationless, relaxation, okay? So remember that fluorescence, sort of is always of lower energy, than absorbance, because some of the energy is actually lost, from radiationless relaxation in the vibrational levels, okay? So light never gets emitted if relaxation is within the vibrational levels. Light is only emitted if the transition is within electronic levels. So let me very quickly, talk about the applications, of emission spectroscopy, particularly, fluorescence spectroscopy. It's very, very sensitive. It's a very, very sensitive technique, because not many techniques out there, rather not many compounds out there, fluoresce. So it's very, very selective and sensitive type of technique. For example, people can use it, and I've used it, to analyze elements, such as selenium in Brazil nuts. But because selenium itself is not very fluorescent, people would often do derivatization like this. So they can take selenium or selenite in this case and react it with a fluorescent compound, such as, this compound here. It's almost a ligand, so essentially it's a ligand, and you end up with a complex that is fluorescent. Okay, so you take selenium, you react it with diaminonaphthalene, it gives you this fluorescent compound, and that's what you analyze using fluorescence. So even if selenium is not fluorescent, you can do derivatization to make it fluorescent. And of course, there are many, many other applications, out there. I just took this as an example, of detection of elements, using fluorescence spectroscopy. It's very common when you're doing calibration with fluorescence spectroscopy to have this situation, where you see an increase, a linear increase with concentration, but at some point, instead of plateauing at the limit of linearity, instead, it decreases. And the reason it decreases is because you've got some of the light that is emitted being reabsorbed, by the elements in the ground state, okay? Remember, at any given level, at any given time, you've got most of the atoms or most of the molecules, in the ground state. So sometimes you've got the light that is emitted being reabsorbed, by the molecules in the ground state instead of being detected. And so that's why you end up, getting a decrease, especially in high concentration, because there's a higher probability, of having more electrons, or rather more atoms in this case, or more molecules, in the ground state. So self-absorption is a common problem, with fluorescence spectroscopy, which limits the dynamic range. Self-absorption is a big problem. So of course, you can see the solution again to this problem is dilution. You can only analyze, low concentrated type of samples. So other than detection, fluorescence has also been used widely for other types of applications, such as, making these fluorescent bulbs, which typically is just a bulb made of mercury. And mercury actually is a fluorescent element. And, when it fluoresces, and you have, these bulbs also containing luminescent substances, such as manganese and antimony, which tends to increase, the light, that is emitted. So you can see the mercury can be excited. It relaxes to give you the UV radiation. The UV radiation gets reabsorbed, by the luminescent substance, and it gives off, the white light. And that's how you end up, with a fluorescent bulb. So you can see fluorescence, other than detection, it's also used for many other types of applications. Again, you can use fluorescence, for detection of many natural compounds out there, like the PAHs, polyaromatic hydrocarbons, which come from fossil fuels. You also have natural products such as vitamins, such as riboflavin, which is naturally fluorescent, and so on. So very important technique for detection with very low limit of detection. Very important technique. In biology, it's also used a lot, for detection of DNA. But in this case, because some of the DNA, or most of the DNAs, they are not fluorescent, often we would tag them or derivatize them, using a fluorescent compound such as fluorescein and so on. So many applications. So other than fluorescence, you also have phosphorescence, but you also have other types of technique of, called chemiluminescence as well. And so chemiluminescence is another type of luminescence spectroscopy that is a bit different from phosphorescence and from fluorescence, okay? With chemiluminescence, as the name suggests, you're getting the emission coming from a chemical reaction. So you do a chemical reaction, such as, you take luminol. If you add an oxidant, such as hydrogen peroxide, you form a complex at an excited state, that releases off light. And so actually chemiluminescence, has been used a lot, for detection of things like hydrogen peroxide. It's very simple. Take luminol, add hydrogen peroxide, it gives off light. Or even take luminol and add something like nitrogen oxides, and it gives off light. And there are many people developing different types of detection techniques using chemiluminescence. So take note of this. So there's no light source. So the light source really is the chemical reaction. Now in nature, you've got, you've got organisms such as fireflies, for example, that give off light. And I've just included it here because in the art of innovation, you've got people looking at nature using the so-called biomimicry approach. You observe nature, see what happens in nature, and then create inventions. And people have studied, for example, how the firefly generates its light as a way, to create innovations, that produce energy devices, or very, very low, high energy devices, that are fairly green, okay? And that's what you call biomimicry, which is a fairly good approach, to do innovations. So fireflies are good classical examples of organisms out there that exhibit chemiluminescence, due to the chemical reactions or biochemical reactions within the organism, giving off light. So as I've said before, you know, the components of fluorescence or luminescence spectroscopies, you know, in general look like that. So take note of the advantages and disadvantages of fluorescence, most of which is sensitivity, which I've talked about, specificity, you know, and so forth. And one disadvantage, of course, you know, not too many compounds out there that go fluorescence or phosphorescence for that matter. And the solution to that is derivatization. Okay, to make them fluorescent, like the example I gave with selenium. So lastly, how do you do detection? Now there are many types, because of course detection is a major component that limits the limits of detection, or a major component that affects the figures of merit. So how do I count the photons? How do I convert light, you know, that's coming from the sample, be it with emission or be it with transmission? How do I convert it, you know, into current? All right. How do I transduce it? You know, how do I transduce it? A transducer, sometimes they call it a detector. Now, very, very common detector out there for spectroscopy is what you refer to as a vacuum phototube. And a vacuum phototube is very simple. It's just a tube, as the name suggests. And within that tube, you've got an electrode called a cathode. And then the cathode is coated, you know, with what you refer to as a photoemissive surface. And a photoemissive surface would be a surface that very easily ionizes, you know, when you impinge it with light, meaning it undergoes what you refer to as a photoelectric effect, meaning when light hits on that coating, the electrons in the outermost level, the valence electrons, you know, get ionized, you know, they get ionized. And so you're detecting, you know, those electrons. And so that is what you refer to as a photo, meaning a photon hitting a photoemissive surface to give off electrons. So you can see it's ionization, you know, that is taking place. Now, surfaces that very easily ionize, as you can easily tell, would be made from alkali metals. So alkali metals are very easy to ionize. Maybe you guys should go and check. The ionization energy of the alkali metals is very, very low because I've got only one electron, you know, in the outermost level, and so it's very easy, you know, to dislodge, you know, that electron. And so that's why photoemissive surfaces, you know, are made with alkali metals. And so the most common detector out there is what you refer to as a vacuum phototube. And I hope I've shown you, you know, how to explain, you know, how it works. A photoemissive surface, light hits of that photoemissive surface, the outer electrons are dislodged or ionization happens, and then you can measure the current, you know, that is resulting. That will be proportional to the amount of light or the light intensity that impinged on the photoemissive surface. Now, to increase the sensitivity of the vacuum phototube, sometimes people just combine many vacuum phototubes inside a tube, and sometimes they call them diodes. You know, so each individual phototube, sometimes called diode, is put within a tube, and that way, you know, you are able to increase the light the electrons, you know, that is resulting. For example, I've got light impinging on the first diode. It creates electrons. Those electrons are accelerated to the next phototube. And so instead of, you know, light hitting the second phototube, in this case now I've got electrons. And equally, electrons can cause more ionization. So it causes more ionization, and those electrons are accelerated to the other phototube, and so on. And so in the end, I've got an avalanche of electrons. And that is what you refer to as a photomultiplier tube. And as the name suggests, I've just multiplied the number of phototubes that are present. Okay? And that way, again, I get a very high sensitivity. Very high sensitivity. Meaning from just a very small amount of light, I can amplify the current that is generated, because of these multiple secondary impeachments, that are happening in the secondary dynodes. So take note of that, how the photomultiplier tube works, which is just simply a phototube, and I've got multiple or multiplex of phototubes. So there are many detectors out there, for different, and I've shown this slide before. So you can see, I can have an absorbance type of system for detection, right? I can have fluorescence system, for detection. I can, and of course you can see all those, are good examples, of spectrometer that are typically used, of course, with chromatographies, for detections, and among others, such as mass spectrometer as well. It's very similar, to optical spectrometers as well. Because the mass spectrometer really, you can see the difference. The energy source in this case, is the ions. So I've got the ions. And the ions in this case, they are going through a way to separate those ions, and then I've got a way to detect those ions. And that is the basis, of mass spectrometers. But I don't have a lot of time to talk about mass spectrometers, and I've got only have this slide here just to show you, and I'm gonna do this in other higher level courses, the different types of mass spectrometers which compete, with optical spectrometers as detection tool. And there are many types of spectrometers out there, like the magnetic sector, among many others, but very expensive techniques in this case. So that's all that I'm gonna say, about spectrometers. And I hope I've clarified, the basic theory behind the spectrometers and the different components that are present in the absorbance spectroscopy, fluorescence spectroscopy, and phosphorescence spectroscopy, and of course chemiluminescence, which doesn't have a light source again, because the light is purely coming from a chemical reaction. And so that's all that I'm gonna say about spectroscopy. And that brings us to the end, of the lectures in this course. I think we've done reasonably well. I hope all of us feel like we are finishing fairly strong. And the next thing for me is to thank you for being diligent in the course, and I wish you the best of luck in your final exam, which is gonna be on the 18th. If I can mention very quickly about the final exam will be an open book, and all the questions really are gonna come from the notes, okay? So you don't have to really worry, you just need to really revise the notes. And because it's an open book exam and you've got the notes and the video lectures and so on, it makes no sense for me really to post a new problem set, especially for the theory sort of segment that we covered from potentiometry to the end. However, remember, it's going to be a comprehensive exam. It's going to be comprehensive, meaning everything we've covered, from the beginning is going to be tested. It's going to be tested. Again, it's an open book exam. Now, the exam will be made available on the 17th of December at 1 p.m. and it should be submitted through Blackboard on the 18th of December at 4 p.m. and that's going to give you slightly more than 24 hours to complete the exam. And again, I wish you the best of luck. I'm going to be available during the normal office hours on Wednesdays and Fridays you know, typically at 3:30 p.m. I'm gonna be available today as well as next week, and until really you do your exams, I'll be available to answer your questions. Again, I'm very happy with all of you that you've done fairly well, in navigating, through this course. Best wishes.